Look up at the night sky. You can see stars, planets, galaxies. Beautiful. But here is something strange. Everything you can see. It is only 5% of the universe. The other 95% is invisible. We cannot see it. We cannot touch it. But we know it is there. Today we are going to talk about dark matter. What is it? How do we know it exists? And why does it matter? Let us start at the very beginning. Not with dark matter itself, but with gravity. Because dark matter was discovered through gravity. Gravity is the force that pulls things together. Every object that has mass pulls every other object toward it. The more mass an object has, the stronger its gravitational pull. A mountain pulls harder than a pebble. The sun pulls harder than the mountain. This is why planets orbit the sun. The sun's gravity keeps them locked in a curved path, like a ball on a string. Now here is the key idea. If you know how fast something is orbiting, you can calculate how much gravity is pulling it, and therefore how much mass is at the center. Scientists used this exact logic to study galaxies. They measured how fast stars orbit around the center of a galaxy. And what they found was impossible. Let us think about our own galaxy, the Milky Way. It is a giant spinning disk of stars, gas, and dust. Everything orbits the center. Most of the visible mass, the stars, is clustered near the center. So you would expect stars near the center to orbit fast, and stars on the outer edge to orbit slow. Think of it like our solar system. Mercury, which is closest to the Sun, moves very fast. Neptune, far away, moves very slowly. This is exactly what gravity predicts. So in the 1970s, an astronomer named Vera Rubin decided to measure how fast stars orbit in galaxies. She expected to confirm exactly this pattern. But when Vera Rubin looked at her data, the stars were not slowing down. Stars on the outer edges were moving just as fast as stars near the center. This is called the galaxy rotation problem. The outer stars were moving too fast. If only the visible mass existed, those stars should have flown off into space long ago. But something was holding them in place. Let us talk about Vera Rubin for a moment, because her work changed astronomy forever. Vera Rubin spent years carefully measuring the rotation speeds of dozens of galaxies. Not one galaxy. Not two. Over 200 galaxies. Every single galaxy showed the same result. Outer stars moving too fast. The rotation curve was flat, not dropping. This was not a mistake. This was not a fluke. This was a pattern, a law of nature that nobody could explain. Scientists had two choices. Either our understanding of gravity was wrong, or there was mass in the galaxy that we simply could not see. Most scientists eventually agreed, there must be extra mass. Mass that is invisible. Mass that does not emit or reflect light. They called it dark matter. Now, when scientists say dark, they do not mean it is black or shadowy. They mean it is completely invisible to all light. Normal matter, like you, the stars, this screen, interacts with light. It absorbs it, emits it, reflects it. That is how we see things. Dark matter does none of this. Light passes straight through it, like dark matter is not even there. That is why we cannot see it with any telescope. But dark matter does have mass. And mass creates gravity. So even though we cannot see it, we can feel its gravitational pull. That is the only way we detect it. Think of it like wind. You cannot see wind. But you can see the leaves move, the trees bend, the flag wave. Dark matter is like wind, invisible, but its effects are visible. The galaxy rotation problem was just the first clue. Scientists found a second, even more powerful piece of evidence, called gravitational lensing. Here is the idea. Einstein showed us that mass bends space. And when space bends, light bends too, like a lens. So if a very massive object sits between us and a distant galaxy, the mass bends the light from that galaxy toward us. We can see more light than expected. This bending creates a visual effect. The distant galaxy appears stretched, distorted, or even split into multiple images around the massive object. Scientists measure how much the light bends. That tells them how much mass is doing the bending. And here is the problem. The visible mass is never enough. The amount of mass needed to cause the observed bending is 5 to 6 times more than all the visible stars and gas combined. The missing mass is dark matter. Now we come to the most convincing evidence for dark matter we have ever found. It involves two galaxy clusters, crashing into each other. A galaxy cluster is a massive group, hundreds of galaxies, plus enormous clouds of hot gas. The gas is the heaviest normal matter component. When two galaxy clusters collide, something interesting happens. The galaxies, which are mostly empty space, pass straight through each other with almost no collision. But the gas clouds interact. Gas is physical. It crashes, slows down, heats up, and gets left behind in the middle of the collision zone. Now, if there were no dark matter, the heaviest part, the gas, should also be where most of the gravity is. But scientists measured using gravitational lensing, and the gravity was not in the middle. The gravity was in two separate regions, one on each side, exactly where the galaxies had moved to. Something massive had passed through with the galaxies. Dark matter does more than just hold galaxies together. It is the reason galaxies exist at all. Let us go back to the very beginning, just after the Big Bang. Right after the Big Bang, the universe was a hot, smooth cloud of gas. It was almost perfectly uniform. No clumps, no galaxies, just gas. But dark matter was already there, and it was not perfectly smooth. There were tiny regions with slightly more dark matter than others. Gravity then did its job. These slightly denser regions pulled in more gas. More mass meant more gravity. More gravity pulled in even more gas. A feedback loop. Over billions of years, these clumps grew bigger and bigger, eventually becoming the seeds of galaxies and galaxy clusters. Without dark matter, normal matter, which was smooth and uniform, would have spread out forever. There would be no galaxies, no stars, no planets, no us. Scientists have mapped how galaxies are arranged across the universe. What they found looks like a giant web, called the cosmic web. Galaxies cluster along these filaments, long strands of matter stretching across hundreds of millions of light years. Between them are vast empty voids. This entire structure, the filaments, the clusters, the voids, was shaped by dark matter. Dark matter formed the scaffolding first, and normal matter followed. Computer simulations that include dark matter produce webs that look exactly like the real universe. Simulations without dark matter look completely different, wrong. We now know roughly how much dark matter there is. And the numbers are staggering. Let us look at our own galaxy first. Every galaxy is surrounded by a huge invisible sphere of dark matter called a dark matter halo. The halo extends far beyond the visible stars. For the Milky Way, the visible mass, all the stars and gas, is about 10% of the total mass. The other 90% is dark matter in the halo. Across the whole observable universe, dark matter makes up about 27% of all energy and mass. Normal matter, everything we have ever seen, is only 5%. And right now, as you watch this, dark matter is passing through you. Through the walls. Through the earth. Completely silently, with no effect. So what is dark matter made of? This is the biggest open question in physics. Scientists have several candidates, but none confirmed yet. The most popular candidate for a long time was something called a WIMP, a weakly interacting massive particle. A new type of particle, heavy, and barely interacts with normal matter. WIMPs are attractive because they come out naturally from theories of particle physics. Physicists expected the Large Hadron Collider to find them. So far, no WIMPs found. Another candidate is the Axion, an extremely light particle. So light, in fact, that billions of them would weigh less than one electron. Axions interact so weakly with normal matter that they pass through everything. Experiments are being built specifically to try to detect them, using powerful magnetic fields. A third candidate is the sterile neutrino. A neutrino is a real particle we already know about. It barely interacts with normal matter. A sterile neutrino interacts even less. None of these candidates have been confirmed. Dark matter remains one of the greatest unsolved mysteries in all of science. You might be wondering, if dark matter is everywhere, why is it so hard to detect? The answer is in how it interacts. Normal matter interacts through four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Dark matter, on the other hand, only interacts through gravity. It does not interact with light, that's why we cannot see it. It does not interact with the strong nuclear force, that's why it does not form atoms. It barely interacts with the weak nuclear force, that's why it passes through normal matter like a ghost. The only way we know dark matter exists is through its gravitational effects on galaxies and light. This makes detecting it directly extremely challenging. Scientists have built underground laboratories, trying to catch a dark matter particle as it passes through. So far, despite decades of searching, we have not caught a single one. There are several major dark matter detectors running right now around the world. Let us look at a few of the most important ones. In the United States, there is Lux Zeppelin, one of the most sensitive detectors ever built. It is located deep underground in South Dakota, shielded from cosmic rays. In Italy, there is Xenon-1T, located beneath the Gran Sasso mountain. It uses liquid xenon to detect any dark matter particles that might pass through. In China, there is Panda X, located in the Jinping Underground Laboratory. It is one of the deepest underground labs in the world. These detectors are incredibly sophisticated, costing hundreds of millions of dollars. They operate in complete darkness, waiting for a single flash of light that might signal a dark matter interaction. So far, they have not detected any dark matter particles. But the search continues, because finding dark matter would be one of the greatest discoveries in physics. Some scientists ask, what if dark matter does not exist at all? What if our theory of gravity is simply wrong at large scales? This idea is called modified Newtonian dynamics, or MOND. It suggests that gravity behaves differently when it becomes very weak. Instead of dark matter pulling on galaxies, gravity itself would be stronger than we expect. MOND can explain some observations without needing any invisible matter. However, most physicists are skeptical. MOND struggles to explain the bullet cluster and other observations that seem to show dark matter clearly. The consensus remains, dark matter is the best explanation we have. But the question reminds us to stay humble. We do not know everything about the universe. People sometimes confuse dark matter with dark energy. They sound similar, but they are completely different things. Let us clear this up. Dark matter makes up about 27% of the universe. It pulls things together with gravity. It has mass. It helps form the structure of galaxies and clusters. Dark energy makes up about 68% of the universe. It pushes space apart. It has no mass. It causes the expansion of the universe to accelerate. Dark matter pulls. Dark energy pushes. They are not the same thing at all. Let us come back home to our own galaxy and think about dark matter in a very concrete way. Right now, the Milky Way is swimming in dark matter. Our galaxy is embedded in a giant halo of invisible matter. This dark matter halo is much larger than the visible galaxy itself. It extends far beyond the stars we can see. The dark matter is all around us right now. It is passing through you as you watch this. Billions of dark matter particles are flowing through your body every second. You cannot feel them because they barely interact with normal matter. But they are there, creating the gravity that holds our galaxy together. Without dark matter, the Milky Way would fly apart. The stars would scatter into intergalactic space. We owe our existence to this invisible substance. If dark matter is a particle, Could we create it in a laboratory? This is exactly what physicists at the Large Hadron Collider have been trying to do. They smash protons together at nearly the speed of light. The hope is that in the debris, a dark matter particle might appear. It would escape the detectors without a trace. We would know it existed only by the missing energy it carried away. There is a third way to search for dark matter: indirect detection. The idea is that dark matter particles might occasionally annihilate each other, releasing energy. When two dark matter particles meet, they could destroy one another and produce gamma rays. Telescopes like Fermi scan the sky for these telltale signals. We look for excess gamma rays coming from dense regions where dark matter should be concentrated. It is a search for the afterglow of dark matter collisions. There is one more fascinating candidate for dark matter: primordial black holes. These are not regular black holes formed by dying stars. These formed moments after the Big Bang. They have all the properties we need for dark matter. They have mass. They create gravity. They emit no light. And they are completely invisible. But there is a problem: we have not found enough of them. Let us go deeper into how dark matter shaped the universe. When we run computer simulations of the universe, we can turn dark matter on or off and see what happens. With dark matter, we get a cosmic web, galaxies clustered along filaments, leaving vast empty voids. Without dark matter, the universe stays smooth and uniform. No galaxies, no stars, no cosmic structure. The real universe looks exactly like the simulation with dark matter. This is some of the strongest evidence we have that dark matter is real. One of the most powerful pieces of evidence comes from the oldest light in the universe. The cosmic microwave background, or CMB. The CMB is a snapshot of the universe when it was just 380,000 years old. It shows tiny temperature variations, hot spots and cold spots, left by sound waves in the early universe. The precise pattern of these temperature variations depends very sensitively on how much dark matter existed in the early universe. Scientists plug in different amounts of dark matter. Too little. Too much. Just right. And match the pattern to the real CMB. The best fit is 27% dark matter. This matches the number from galaxy rotation curves, gravitational lensing, and the bullet cluster. All independent measurements. Same answer. Most models assume dark matter particles barely interact with each other. They just drift past each other. But a newer idea called self-interacting dark matter suggests maybe they do interact. If dark matter particles interact with each other, even slightly, it would change how dark matter halos are shaped. They would become rounder and smoother in the center. Some observations of dwarf galaxies hint that the centers of their dark matter halos are too smooth. Which would match self-interacting dark matter better? This is still a hypothesis, not proven. But it shows how much detail scientists are now exploring in their models of dark matter. The search for dark matter is one of the most active areas of physics. In the coming decade, new experiments and telescopes will dramatically improve our ability to hunt for it. The Vera Rubin Observatory in Chile will photograph the entire visible sky every few nights. It will map gravitational lensing across billions of galaxies. The most detailed dark matter map ever. The Euclid Space Telescope, launched in 2023, is already mapping the three-dimensional structure of the universe, tracking how dark matter shapes galaxy clusters over billions of years. Meanwhile, underground detectors are being made more sensitive. The next generation of xenon detectors will be sensitive enough to detect even a single nucleus recoiling from a dark matter hit. There is also a new approach, using quantum sensors. These are devices so sensitive they can detect vibrations smaller than an atom. They could pick up dark matter interactions that all previous detectors missed. Here is an honest question. What if we run every experiment, build every detector, and still never find the dark matter particle? What then? That would be extraordinary, and it would force us to rethink physics. It would suggest that dark matter is something far stranger than any particle we have imagined. Some theorists propose dark matter could be part of a hidden sector, an entirely separate set of forces and particles that do not interact with our matter at all, except through gravity. In this picture, there could be dark atoms, dark molecules, even dark chemistry, but all completely invisible and unreachable from our side. This sounds like science fiction, but it is a real area of theoretical physics research. It reminds us that we should not assume dark matter must look like what we already know. Let us step back and think about why dark matter matters. Not just for scientists, but for how we understand our place in the universe. For most of human history, we assumed the universe was made of the same stuff we are made of: stars, rocks, gas. Matter that we can see and touch. Dark matter shattered that assumption. We now know that the matter we are made of, atoms, molecules, everything in chemistry and biology, is a tiny minority in the universe. This is one of the most humbling discoveries in the history of science. We are not the main character of the universe. We are a small side note. But here is the beautiful part. We figured this out, not by touching dark matter, not by seeing it, but through careful reasoning, observation, and logic. That is what science is. Let us do a quick recap of everything we have covered today, because we have covered a lot. First, the rotation problem. Stars at the edge of galaxies orbit too fast. The visible mass cannot explain this. Extra invisible mass, dark matter, must be present. Second, gravitational lensing. Light bends around galaxy clusters by more than the visible mass can explain. Again, extra mass is needed. Third, the bullet cluster. Two galaxy clusters collide. The gas slows down. The gravity does not. The gravity moves with the galaxies, proof of dark matter that does not interact with gas. Fourth, the cosmic web. The large-scale structure of the universe only forms correctly in computer simulations when dark matter is included. Fifth, the CMB. The pattern of temperature fluctuations in the oldest light in the universe precisely requires 27% dark matter to match what we observe. All 5 of these lines of evidence come from completely different observations. They all independently point to the same number: 27% of the universe is dark matter. Before we finish, let us be clear about what dark matter is not. Because there are many common misconceptions. Dark matter is not dark energy. Dark matter has mass and pulls things together. Dark energy pushes space apart. They are completely different. Dark matter is not antimatter. Antimatter is the opposite of normal matter. It exists, and we can make it in labs. But antimatter interacts with light. Dark matter does not. Dark matter is not a black hole, at least not mostly. While primordial black holes could be a small fraction, they cannot account for all of the dark matter. And dark matter is not just regular matter we have not found yet, like distant gas clouds or dim stars. We have checked. The CMB rules this out. The story of dark matter is also a human story. It is about scientists who trusted their data even when it contradicted what everyone believed. Fritz Zwicky was the first to propose invisible mass in 1933. He studied galaxy clusters and found they were moving too fast. Nobody believed him for decades. Then Vera Rubin, in the 1970s, provided the systematic, irrefutable evidence from galaxy rotation curves. Her work could no longer be ignored. Since then, thousands of scientists have worked on dark matter, building detectors, running simulations, designing telescopes, all searching for the same invisible thing. This is how science works. One person notices something strange. Another confirms it. Thousands more try to explain it. Slowly, the mystery yields to understanding. Imagine the day when a detector finally records an unmistakable dark matter signal. What would that mean for science? First, it would tell us what dark matter is made of. It would add a new particle to the standard model of physics, the first major addition in decades. Second, it would open up an entirely new area of physics. Understanding dark matter interactions could reveal hidden forces, hidden particles, hidden sectors. Third, it might lead to applications we cannot imagine yet. Just as the discovery of the electron eventually led to computers, discovering dark matter could lead to technologies far beyond our current imagination. Of course, we do not know when this discovery will happen. It may be in 10 years. It may be in 100. It may require entirely new ideas we have not thought of yet. We have reached the end of our journey through the dark matter story. But this is not the end of the real story. We know dark matter exists. We know it makes up 27% of the universe. We know it does not interact with light. We know it shapes galaxies and holds the cosmos together. But we do not know what it is. We do not know how to detect it directly. We do not know what secrets it might reveal. The search continues in laboratories around the world. In space telescopes. In computer simulations. The universe is vast, mysterious, and waiting. The next discovery could be yours.